Welcome everybody to the webinar of today. The speaker of today is Nicolas Mazellier, and he's going to talk about the influence of free stream turbulence on the aerodynamics of road vehicles. As usual, I introduce the speaker very briefly, and then I leave him the floor. Nicolas Mazellier is professor of fluid mechanics at the University of Orléans in France. After he received his PhD from the University of Grenoble in France in 2005, he was a postdoctoral research fellow from 2006 to 2007 at Imperial College London, UK, and then from 2007 to 2009 at Korea, Rouen in France. In 2009, he got an associate professor position at the University of Orléans. His research interests encompass the physical modeling and the control of turbulent separated flows and wakes with application in transport and renewable energy applications. He is the coordinator of the European project Perseus. That's grant number 887010. It's a Clean Sky project H2020, and that's dedicated to the design of effective pulse jet actuator for controlling turbulent flows and separations. It's with great pleasure that we host Nicolas Mazellier. So Nicolas, I stop sharing my screen and you can start sharing yours. One second. There we go, we see your screen.
Okay, perfect.
And you're pointed.
Thank you, Francisco, for this introduction, and thank you to all of you for this invitation. I'm very pleased to be here today. I understood that I will be the first one testing this hybrid system, so I hope it will be okay for you also. And today I will present a work dedicated to the influence of free stream turbulence on the aerodynamics of road vehicles. So I will speak about road vehicle at some point, even it will be some models of these vehicles. And the second part of the presentation will be dedicated to the effect of turbulence, external turbulence on the vehicle. This work is made as a part of a French national project funded by the ANR. The project is called Co-Wave, and it has implied obviously more than me. Here I'm speaking about the co-workers on that project from Prism, Azeline Corta, Stéphane Noyer, our engineer, PhD student, Wassim Zedain, and also I will present some results coming from the LEA lab at Nantes, and the numerical simulation was done by Emmanuel Guillemino. Okay, my presentation will be dedicated, decoupled into three main parts. I will speak first about the motivation of the work. Then I will present some results about a simplified road vehicle. It will be a flow around the Hamed body. You will see it later. And then after I will come to the more realistic part of the study, which is dedicated to the industrial model that we have used, which is C4 Picasso from Peugeot. Where we have also imposed some inflow conditions with turbulence inside. So most of the work has been done using experiments, but I will show also some numerical results. So let's first start with the motivations. Here I'm presenting the main contribution to the drag, because here we are looking to road vehicles, so we are interested into the drag for consumption problem, in fact. And if you look the contribution, the aerodynamic drag, which is in blue here, appears to be the dominant contribution when we are at high speeds, so in highway conditions. And if you think that the next generation of cars will be electrical cars, there is a problem of autonomy of this car if you want to make long-range distance, because you will have to use this type of motorway systems. So this is a big deal to be addressed in the future. And most of the car now resembles this one, not necessarily a big car, but a car with a flat back. So like SUV and so forth, to gain in terms of space. And if you look at this one, then you can see that most of the drag, so most of this blue part here comes from the back of a car. 30% is dedicated to this. And that's why we have focused a lot of attention to this part, so the near wake of the road vehicle. If we now look to the near wake of a road vehicle, so this is a simplified one. This is coming from a study we have done with an American team very recently, and it was published in Experiments in Fluids. So here we have the back of a Hamed body. You will see it later also. But this body here has a 25-degree slant angle at the end, and the flow is coming from bad parts and goes from bad parts. And you can see that the topology of the flow is very complex with massive separations. For example, here where we have the separation at the base, but also separation and reattachment points, for example, for this typical example. And with the release of lateral vortices, tip vortices type things. So the flow is very complex in terms of physics and topology. That's why it's changing to address this type of systems. Obviously, when you want to minimize the consumption of your car, you want to introduce some part of flow control to manipulate the flow to reduce the drag. This is the objective at the end for the industrials. So at the laboratory scale, it is okay. Here I'm presenting some studies that we have done in Orléans 10 years ago about where we have imposed pulse jets at back position, for example. And doing this, you can see that here is the drag evolution when we use flow control systems. And you can see that 0 means there is no evolution compared to the reference case, whereas when you are going to the negative part, you reduce the drag of your system. So you can see that we can reach up to more than 10% of drag reduction quite easily using this type of system. And here another example done at Orléans with separate plates here at the rear part of the car, where here again you can achieve about 10% drag reduction with these simple systems. So now we have been able to gain drag at the laboratory scale, but what will happen when we go to the real scale? And here is a comparison between an experiments done by Pujals and co-workers using some vortex generator elements on the top part of the car. So the flow is coming from here and goes to this part. And here it's an upscaling model using the same type of systems. So here is the results of these lab experiments, where you can see that still, if you configure properly your system, so you displace the elements compared to each other and you position them at the right position, then you can have up to 10% drag reduction. Okay, so we take this one, we just make an upscaling of the system. So here it's a real car, and then you've got drag increase. So that's a problem, because at the end of the day, the consumption of this car is important for you. So we need to understand what's happening from that to that. And it means that we still need a more physical understanding to be able to make this upscaling problem. And this asks a question of, is there any possible unifying framework that can be true for that lab experiments and that real life experiment? So that's what we have tried to do during these projects, particularly. And the main, let's say the main philosophy that we had is to say, okay, when we act on the flow, we are making a forcing. This forcing has the objective to change the aerodynamic loads. So in our case, reduce the drag. And one mechanism to do this is to modify the separated shear layer, which are released at the back of the curve. So these shear layers are here, and they are coming from the separation of the, for example, top boundary layers in this scheme. So if we look more carefully, this element here and this element here are very close to a famous image that we had from the past, from the Brown and Roscoe study, where we see a shear layer developing we see some elements of coherent structures inside, plus an additional turbulence, which is on top of it. And one of the main elements that we want to control in that system usually is the size of this shear layer. And more especially, we want to control the growth rate of this shear layer. So at which speed this delta omega is growing in space, for example. So if I want to, for example, minimize the bubble of recirculation, I would like to increase the growth rate. Whereas if I want to increase the size of the bubble, I want to decrease the growth rate of my shear layers. So the growth rate is usually something that we want to control, and this is something not specific to the car system. You can find for any wakes problem. Also, you can have some problem of coupling in that case also, because you have a top shear layer, a bottom shear layer, and also sides shear layers. So the problem is more complex than only looking to one shear layer and so forth. And there is another question which is still open now. How this growth rate and coupling system is depending on the geometry. So if I change the shape of the car, are my shear layers different or not? Do they grow differently also, and so forth? And also other problems like if now I had on top of this flow turbulence conditions, which represents what is in real life systems, in fact, what will happen for the development of these shear layers? And these are still open questions that needs to be addressed. So the way we have addressed this problem is by looking at what we will call turbulent entrainment. I will not speak too much of the turbulent entrainment today because it's not the focus on my talk, but it is the global view that we have behind it. And this is not something new. I mean, turbulent entrainment has been studied for years and decades now, and still it is a mechanisms that could be used to explain all of this system that we have here. What is turbulent entrainment? It's no more than the transport of a quantity through an interface. So this quantity could be mass, and in the past in our team, we have worked a lot about mass entrainment through flow separation. But if we now think about forces, because at the end of the day, here we want to control a force, then we need to think about momentum entrainment. And now if we want to optimize the energy of the system, then you would like to see how the entrainment of energy is doing into that system. But you can apply this type of concept to any other quantities, like concentration, like reactant, if you are making combustion, and so forth. So here I'm showing a very famous example of turbulent entrainment. This is applied for a wake. It comes from a study by Philip and Mazellier. And you can see that the red part is the average interface of your wake, whereas the gray part represents the instantaneous interface. And you can see that obviously the instantaneous interface is much more complex compared to the red one. And the physics is what's happening here, where you will have parts which are large scale parts. So we will speak about engulfment in that case. And on top of it, you will have very small whirling process, which is connected to nibbling process. At least that's like this, that Corsin introduced this concept in the past. So you'll see this is very complex. I will do things much simpler than this. So if you will look like to turbulent entrainment, we need to think about, okay, which quantity do I want to entrain and do I want to study, to investigate? At what scale? Because here you see that the problem is a multiscale problem, which is making the problem very complex. And through which interface? Because you can define any kind of interface based on a certain quantity, in fact. So let's speak about the first two questions. So the quantity and the scale at which we will look at its quantity. So here we are looking to forces. As I said, here we are interested into the drag of a vehicle. So if I want to speak about the drag, I need to speak about the momentum. So the momentum equation will be for me the equation on which I will rely. And at what scale? Here today, I will speak about mean drag. So if I make a distance of 100 kilometers, I will consume a certain amount of energy to do this, a certain amount of fuel, and then this will be connected to my mean drag process. So here I will speak about mean drag, and this is the mean momentum transport equation written in a dimensionless process. I will come back later on this. So, but this is the two first questions. Now I need to address the last one, which is what is the interface I will select to look at this momentum equation, because here it's an integral form of this interface of this equation, where I need to define what is the contour C on which I need to process my flow. And there is plenty of choice to make this. One of the most famous in the past was the TNTI, which is the turbulent non-turbulent interface. And it is something that has to do with this schematic here. But now if we think about, if we now add turbulence in the external flow, we need to think about turbulent interface, which is a tricky problem in itself. So I will just remove this type of interface for this analysis. Another solution will be to use a separatrix interface. So that would separate the streamwise direction to the anti-streamwise direction. But when we are looking to 3D flows in experiments, that's not so easy to define this type of separatrix. So I will use another type of interface on which we have worked quite a lot in the past few years, which we call it the recirculation region interface. And this will separate, it is called RRI in the following. And this interface is the limit where the streamwise mean velocity is equal to 0. So it is very easy to be defined. It exists every time. We can define it in 2D. In 3D, there is no big trouble with this. So in the following, I will focus on this one. And here we have an example behind. This is the base of a Hammett body, so a wake of a road vehicle. The flow is coming from here and goes to here. And here you see a typical reconstruction in 3D in an experiment we have done of this recirculation region interface. Okay, so we have the problem, we have the way we will address the problem. And now it is the strategy on which will we trust to get to some kind of new insights. So the strategy of the CoWave project has been to start with a very simplistic model of a road vehicle. And this has been used for years and years, which is the Hammett body. Then we move to, I will call it an industrial model. So it's a small model, but the shape of the model is much more realistic compared to this one. And on top of this industrial model, because the industrial model is this one, obviously. And on top of this, we will use free stream turbulence. So it's like this schematic here, where we will have a recirculation double, which is here. And on top of this, we will have a turbulent flow at the external position. Okay? So let's move now to the second part of the presentation, where I will speak about the simplified road vehicle model. Here is the experiments that we have used. So this is the wind tunnel that we have in Orléans, which is a bit lower compared to the one we have here in Lille. So the test has been done in this test section, which is 2 meters by 2 meters wide and 5 meters long. This is the image of the Hammett body that we have used. So it's a flat back Hammett body. So it's like an SUV, let's say. And here you have the dimensions. So the length is about 1 meter. The height is about 290 millimeter. The width is about 400 millimeter. And the ground clearance here is 50 millimeter, which is the original experiments done by Hammett at that time. The experiment has been made at 40 meters per second for the free stream velocity, which leads to a Reynolds number about, which is about 7 times 10 to the power 5. And in these experiments, we didn't use any, at least today, I'm not presenting this one, we didn't use any turbulence in the inflow. So the residual turbulence of the external flow is 0.4%, which is almost nothing. So here we'll call this no free stream turbulence, and in following, it will be no FST. So I'm reminding you that I want to study this equation, and the star in this equation means that we have used a normalization using u infinity as the velocity scale and h the height of the model as the typical length scale. This is a choice. We can make other choice, but this is our choice. Okay. Let me go back a minute on this. To study this, I need to access to what? The mean flow. I need to access to the turbulent part of the flow. So in an experiment, we will use PIV systems to get to these two types of information. This is very easy, let's say. And we need also to get pressure information. And this is more tricky when we are making experiments. So that's why here we have coupled these experiments with a numerical simulation, which is, let's say, more, which is a complementary tool to study this system. So here are some details about the experiments. You can see here the red dots represent pressure taps at the base. So we have 81 pressure taps at the base. This model is put on a forced torque balance to get the drag, because this is at the end of the day, this is what we want to focus on. We've made also outlier measurements. I will not speak about this today here. And more importantly, we have used PIV measurements, so 2D to C measurements, only in the mid-plane. So this is represented here by the red square, which is here, at low frequency. And not so high resolution, let's say. With 3,000 image pairs to compute the mean quantities, because at the end of the day here, we have mean quantity and average quantities for the turbulence, okay? So I need to have statistical averaging to be done. From the numerical part, so this part has been done at the LEA at Nantes. It was done by Emmanuel Guillemino using the EASYS CFD solver. We've used two types of simulation. Reynolds simulation based on K omega SST model. So this is very basic. And another one, which is an hybrid Reynolds LES. So sometimes it's called DES. So here it's a DDES for detached AD simulations. And after we can find plenty of letters to have all those models inside. So here it will couple the advantages of Reynolds close to the walls and advantages to LES far away from the wall. Let's say it like this. So the domain is much larger compared to this image here. It is smaller compared to the wind tunnel experiment itself, obviously. Here are some details about the mesh. So here we are using 50 million cells to mesh the whole domain. And here are some details about the resolution of the simulation. So you can see that the resolution of the simulation is a little bit better than the experiments, but not by a factor of 10. And this is the timescale part. So here the difficulty was to get this type of long time simulation to get bistability effect. I will not speak about this today. Okay, so here we have a lot of information together, and we will try to couple all of them to say, okay, already are my tools relevant to study this type of flow? And I will use the experiments as the reference. Okay, so first question I will ask is to say, are my numerical system relevant to study this flow? So to do this, I will use different metrics. This metrics will be the boundary layer thickness taken at that position here, because it is important to be sure that the boundary layer is the same in the experiments and in the simulation, because it's the initial condition of my separated region. So if I'm making a mistake about the initial conditions, that for sure that the rest of the flow will be different. Another metric will be investigated using the PIV measurements, where we will look at the recirculation region. So you see here, the dashed line represents the limit of a recirculation bubble. And I will define its length. The length is the distance between the base, so this part here, and the maximum point of my bubble, okay? And the last one will be the drag, because at the end it's a macro element, which tells me, is my system efficient in terms of aerodynamics? So the drag will be measured using the balance for the experiments. So if we make a comparison of all these elements, all these metrics between experiments and simulation, these are the results. So here I will present the Reynolds number based on the momentum thickness of a boundary layer, the incoming boundary layer. Here it's the drag coefficient, and here it's the length of recirculation. This is for the PIV, this is for the hybrid Reynolds LES approach, and this is for the Reynolds approach. You can see that if we look at RE theta, they are almost close to each other with a difference which is less than 3%, which is okay. We can say that at least the initial condition for all of this flow seems to be the same in average, obviously. If we look now to the drag coefficient, you can see that the PIV and the hybrid Reynolds LES are very close to each other. There is a difference of 2% only, which tells us that, okay, that's a nice tool to look at this quantity. And if we look to the Reynolds approach, it is much worse because we have already 7% of difference with the experiments. And now if we look to another quantity, which is the length of the recirculation bubble, and here you have the image, the mean recirculation bubble coming from the experiments, the one coming from the hybrid Reynolds LES, and the one coming from the Reynolds LES. You can see directly the difference. These two ones here looks pretty much close to each other, whereas this one is very different in shape and also in length. So here we have a difference between this and this one in terms of length by 7%, which we can say it's bad, but not so bad finally. And this one here has a length which is 30% longer compared to the experiments. So this tool here seems to be very irrelevant to analyze this type of flow. I will use it still for the rest of this part, but we need to be aware about this. Also, I'm taking attention about the fact that you can see that the experimental recirculation bubble seems to be very symmetric between what I will call the upper part, which is here in blue, and the lower part, which is here in red, where we have here the limit is the point of the maximum length of my bubble. The same appears for the Reynolds LES approach, whereas this one is asymmetric. We see that the upper part, it's much longer compared to the lower part. This will have effect in the following. So now I'm calling back the equation I want to solve. So I want to solve this equation here. And here I will use the recirculation interface, recirculation region interface, sorry, as my contour of integration. But I said that this interface is characterized by the fact that the streamwise velocity, the mean streamwise velocity, is equal to 0. So using this and projecting this equation along the x direction, because I want to look at the drag, so the drag appears on the x direction, then this term here, the mean term, disappears, because u, the only term which is coming here, is equal to 0 at that interface. It remains only two terms, a pressure term and a turbulent term. And along the x direction, I will get this equation using this projection system, where the local curvature of my interface will be connected to a normal n that I can project along z and along x. All right? So doing this, I will get this equation where the base pressure, so what I call CPB, so the pressure that my body is experiencing at the base, is equal to these two integrals, where here I will decompose the first term into a normal term, let's say. So a pressure plus the corrections coming from the normal Reynolds stress along the streamwise direction. And the second term here, which is Reynolds shear stress, which is connected to the NZ times DL direction. Okay, let's continue. I will do another things here. I will decompose my interface into two interfaces. An upper one, which I will call it RRI plus, and a lower one, which I will call it RRI minus. Okay? We have seen that it looks very symmetric in that graph, but looking to the upper part and the lower parts, I will see if there is any asymmetry due to this choice. And also, if I'm putting turbulence into my system, so in the external part of the flow, the turbulence I will have on the upper part will be surely not the same as the turbulence I will have on the lower part. So doing this, I will try to see the asymmetry of the shear layers. And here, my expression that I have here will tell me about the influence of a physical variable, so pressure and Reynolds stresses, as well as the flow topology, because the way the Z is evolving, so the shape of the bubble will tell me something about the drag at the end of my system. So the objective is to say how this guy is evolving using these equations. And this guy is directly connected to the drag of my body. This has been shown in different studies. Here I'm speaking about Lorite, Diez, and the co-workers, and Passagia and co-workers, where we have a linear relationship between this base pressure and the drag. Okay, let's continue. Let's look first to the pressure effect. So the pressure effect, so I'm not looking to the second part of the integral here. I will focus here only on the numerical simulations because it's a bit more tricky to get it from the experiments. So this, here I'm presenting the cumulative integral of the pressure as far as I'm traveling along the interface. So at the end of the day, if I'm going from that point to that point, I will look at the value in blue coming from the upper interface, in red coming from the lower interface. And if you look at this equation, the difference between these 2 points, so between this point here and this point here, will give me the total contribution of this term to the base pressure and so to the drag. All right? But I'm looking here also to how this term is built as far as I'm traveling along the interface here in blue and along this interface here in red. So when the red part is positive and the blue part is negative, and if I make a difference, this tells me that this term here will have a positive effect. It will increase the base pressure. So if it increases the base pressure, it decreases the drag. So here, the green rectangle tells me where this term is decreasing the drag. At the opposite, when the red term is negative and the blue term is positive, it is the opposite effect. I will reduce, so I will make a suction effect on the base. And if I make a suction effect on the base, then I'm increasing the drag. So I will separate here regions of positive effect on the drag in green and negative effect on the drag in red. And also we can see that on that curve, there is a crossing between these two terms. So they cancel each other at that position. So I will call it neutral point. there is no effect on the drag. It doesn't change the drag at that position. Okay, so taking this in mind, we can see that there is a huge difference between this hybrid Reynolds LES approach and this Reynolds approach, because here we have the pressure that will have, at the end of the day, a negative effect on the drag. Whereas if you look to this one, it tells you that at the end of the day, the pressure will decrease the drag. So completely bullshit. Now, if we look to the second term here, which is the Streamwise normal stresses, Reynolds stresses, then you can see that, so we can get it from the experiment. So here we have now the column of the experiments. Still we have here the hybrid Reynolds LES approach, and still we have here the Reynolds approach. You can see that this one and this one looks very much the same compared to this one, which is very different. And you can see that we still have the same type of evolution, let's say. We have a first part where, in that case, this term of u prime square will increase the drag. And then there is a cancelling effect where we have this neutral point. And then we have this term which will play on drag reduction. So we have the same effect here. And in a sense, this term here will fight again the pressure effect. Okay? Let's continue on the last term, which was coming from the Reynolds shear stress. Here I'm representing the evolution of the Reynolds shear stress along the upper interface, along the lower interface. So for the experiments, the simulation, let's say the DDS simulation and the Reynolds simulation. Here I have used these lines in black and put it on all of this graph to show the difference between these three types of approaches. And we can see once again that the hybrid approach is very close to the measurements done by the PIB, whereas this one is completely different. And if we look to this one, we still have, once again, two regions. One where, in that case, the first part of the bubble is making drag reduction, whereas the last part of the bubble, which is much bigger here, makes drag increase. So this term here, at the end of the day, will implement more drag than the others. So if I make a summary of all of these results, so this was to present the methodology and the tools that we are using to try to understand who is doing what, in fact, in that flow. We have the pressure effect, which at the end of the day, so if I'm comparing these 2 points here, will implement drag increase. The opposite will happen for the streamwise normal Reynolds stresses that will have an effect on the drag by decreasing the drag. So these two guys here are compensating each other in a sense. And if we look at the Reynolds shear stress, then this one has, at the end of the day, so on the entire bubble, it will have a negative effect on the drag. It will increase the drag, in fact. If we look these points, which are shown here by this dashed line, so my neutral points. So when I'm on the bubble before the neutral points, you can see that all of them are symmetric. I mean, the effect on the upper part of the bubble and the lower part of the bubble is completely symmetric. Whereas if I'm looking now to what's happening after these neutral points, then I will have asymmetry appearing for the pressure and for the u prime square term, and the dominant term will be the upper shear layer, which means that if now I'm implementing turbulence outside of the bubble, then I may have effect on the upper part. And since this upper part is dominant, maybe I will change what's happening for the drag. That was the philosophy. Whereas if we look to the last term, which is very different from the others, we still have symmetry even after the neutral points. So let's go now to the last part of the talk, which is dedicated to the industrial model investigation. So now, as I said before, we have started from a very simplistic model, which is the Hamed body. We now go to a more realistic one, which is a C4 Picasso model at a small size still, but it is more realistic. And on top of it, we will implement free stream turbulence. So the question will be very simple. The trend that we have seen before, are they valid even if we go to more realistic conditions? So first of all, let's compare the models by themselves. So here you see the dimensions of this model. So this one has been provided by, it was a PSA group before, now it's a Stellantis, they change often. And you can see that the typical lengths of this model are comparable to the previous one. Yes, I need to precise that there is no mirrors. And also the wheels are not moving. It's already complex, so we didn't want to use even more complex things. I will have just, so I'm making experiments, so I'm not very, I'm not making videos with nice colors and so forth. I will just show you the experiments. So here is the building where we have the wind tunnel. And here are our experiments. So here you see the wind tunnel. So it's 2 meters in that directions, 2 meters here, 5 meters long. So here you see the C4 model. Let's go inside. So here it's a fan of the wind tunnel. Up. Okay, and I wanted just to show you also. Oh, you see all these white dots here are pressure taps. So we have made plenty of them to know how the pressure is distributed along this vehicle, because compared to the Hamed body, the geometry here is much more complex. So we need to have a very complete view of what's happening on the vehicle. Maybe we can see it also. We have also pressure taps on the top part, all along up to the front part of the vehicle. And also, I'm not sure that we see them clearly, but we have also equipped the car with these taps along the sides of the vehicle. This part here, the rear part, can be removed to implement flow control inside, to put the equipment of pressure scanners and so forth inside. And sorry, let me just close this. And that's all. I'm going back to the presentation now. Okay, so here it's a summary of the experiments and the equipment that we have used to make these experiments. So we still use the 4-stock balance measurements. We have about 150 pressure taps all around the vehicle, and 100 of them are focused on the base of the vehicle. And we have made very long experiments to get a huge number of points. You will see later why we have done this. So each recording is at least 1 hour. So it's a very long experiment to run. We have done also PID measurements with plenty of conditions. Today I will speak about this data set, which is here, which is a high-speed data set. High speed in the sense 50 hertz of laser pulsing. We have a much more highly defined, highly resolved one, which is running in terms of post-processing right now, in fact. So I'm not able to show you this one, so I will show you the results of this one. Okay. Here. And as you can see here, we have used a turbulent generator or not in front of this model. So this is a very simplistic biplanar grid where the mesh is 145 millimeter. The thickness of the bar is 25 millimeter and the solidity is 36%. So that's nothing to do with fractal grids and so forth. Here we are making very simple experimental turbulence. The model is placed about 15 mesh downstream the grid. So the flow is at that position here is roughly homogeneous and isotropic, let's say. Okay. So here you have some typical values important for the understand the difference between the no free stream turbulence conditions and the free stream turbulence conditions. So FST means that we are using turbulence outside the wake. So the velocity will be 30 meters per second. So it's a bit different from the previous one because due to the grid, we have pressure losses. So we cannot reach the same velocity as previously, obviously. But the Reynolds number is not so different compared to the previous case. The Taylor-based Reynolds number is 200 at that position, so which is not so bad to make turbulence. The isotropic metric at large scales is 10%, so we can say that it's nearly isotropic. And here are the turbulent conditions. So the turbulent intensity is 6%. To be compared to the other 4% when we have no grid. So it is significantly different. And the integral length scale at that position here is roughly 30% of the height of the model. These conditions here are very close to what we find in literature about the open road turbulence that we can experience in when we drive. So let's look to first global quantities. Here I will present some results about the side force coefficient. So Fs is the force when we move, when we make a yaw angle on the vehicle. So the yaw angle is beta here, and the yaw angle has been varied between -4 and +4 degrees. And we will look also to the drag, which is defined as previously by this equation. So this is the drag coefficient. So in the following, when I'm using black dots, it means the results coming from the no free stream turbulence. So let's say a laminar flow. And the white triangles will be for the free stream turbulence condition. So you see that for the side force coefficient, we don't see very much effect of the turbulence on the force that the car is experiencing. Whereas if we look at the drag coefficient, then you see that in these particular conditions, we have a drag increase by 4%, whatever the yaw angle we have used. So this means that the main effect, at least what we think it is, the main effect on the flow is what's happening here on the rear part of the vehicle, so on the base. So that's why we will do the same type of wake survey analysis as previously that we have used for the Hammett body. Okay, so I'm reminding you the type of equation that we will use. So we will have an upper recirculation region, a lower recirculation region, which is separated by the maximum point, the length of the recirculation region. And here I'm representing the shape of the bubble that we have in the two conditions. So in black for the no free stream condition, and in white for the free stream condition. Turbulent free stream condition. And you can see that, first of all, we don't see much effect of the main shape of the bubble when we implement the free stream turbulence condition. And also, we can see that there is a strong asymmetry already of the bubble compared to what we have for the Hammett body. That's obvious. If you look to this vehicle, here you have a very different way of the flow on the top compared to what will happen on the bottom. And whereas here we have roughly the same geometry, whatever the side we are looking. So if there is no effect on the bubble itself, can we think that there is an effect on the physical variables? So on the terms pressure, stresses, and so forth. So let's look first on the normal stresses. Obviously, here we are making an experiment. So I will not be able to present any pressure values on in the flow. This is the next step for us to be able to get this. So here will be the no free stream results for the, so this is the evolution of this term along the lower part of the interface, along the upper part of the interface. So blue is the upper, red is the lower. And here it's the cumulation. So the integral as far as it is constructed when I'm traveling along these interfaces. So still blue is the upper part, red is the lower part. So we can see that the Reynolds stresses is dominant on the lower part compared to what we have seen before. And contrary to what we will think, then if we look at the contribution on the drag, so the integral cumulative, it is the blue part, so the upper part, which is dominant. Just because, if you look here, the lower part, there is a flat, a huge part which is flat. So if it's flat, then it will have an action along the Z direction, but the drag is normal to this direction. So what happened here doesn't have any effect on the drag. Whereas if you look here, you have always a curvature. So all of these points here are acting on the drag. So on the mean, these 2 points means it tells you that this term is contributing to drag reduction, pretty much as we have seen for the Ahmed body. Okay, now let's introduce free stream turbulence. So these results on the left are the same as previously. Now on the right, I have the effect of a turbulence. So I have reported dashed lines to for the maximum value, just for you to see it easily, the difference between the curves. So you see that in both cases, the free stream turbulence increase the value of the Reynolds stresses, whatever the upper or the lower part, and it also increases the action on the drag, so the cumulative action that will act on the drag. So at the end of the day, the free stream turbulence will increase the drag reduction. All right, for this term. Okay, now we have the last term of the equation, which is the Reynolds shear stress. Once again, here I'm presenting the results coming from only the no free stream turbulence, so that's a reference case, let's say. Once again, we see that there is an asymmetry into the value of these Reynolds shear stresses. So the lower part is dominating the upper part. And now, since this one is integrated along X, even if I have a flat surface on the bottom, there is no problem. This will contribute to the drag. So this red cumulative term here will dominate its upper part value. And at the end of the day, if you look at this equation, so here I have a positive value of the red part. So this one is positive, so its contribution will be negative. So it will decrease the pressure at the base. Whereas this one, the blue one, the upper part is negative. So it will also decrease the pressure at the base. So on the overall, these two terms here increase the drag. So I still have the same type of mechanisms as previously, but here I lost the symmetry problem compared to the Ahmed body. Now, if I'm, as previously, input turbulence on the external flow, what will happen? Pretty much the same as previously. I will increase the shear stress value, and the effect on the accumulation, the cumulative values will also increase. So my turbulence at the external position will even more increase the drag of my vehicle. So now if I put this all together, here are the drag contribution coming from the U prime squared term, which is the value here from the no free stream turbulence. Here it's the value using the free stream turbulence, and the difference represents plus 25% almost. If now I'm looking to this term, which is here, it will have this value for the free stream turbulence, and this value for the, no free stream turbulence, and it will decrease the drag by 28%, okay? So there is almost a compensation between these two terms. And even, it tells me that in the overall, these terms will decrease the drag. But I remind you that here, I have drag increase at the end of the day. So there is a problem. These two terms here cannot explain by themselves what's happening for the drag of the vehicle. So it means that that's the pressure contribution which is important here. Unfortunately, we don't get it from the experiments. We've made some simulation. I'm not presenting them because they are horrible compared to the experiments. So I will continue on the pressure, but I will not continue on that analysis using the momentum equation. I will just focus on what's happening now on my base of the vehicle. Is it still okay, Francesco?
Yes, yes. Maybe you can wrap it up in 5 minutes or.
Okay, that will be enough, I think. Okay, let's see here. Here it's pressure. So this is minus pressure at the base. So when it is positive and high, it contributes to drag. So it increases drag. Where it's low, it doesn't contribute so much to the drag, in fact. And this is the RMS of pressure. You can see that there is a sort of two regions effect. I'm not sure what you see. Oh, yes. There is an upper part effect and a lower part effect, certainly due to the fact that the shear layers are different from the top and the bottom. And it's even more evident on that part here, where we have almost no fluctuations compared to here what's happening here. If I look to very located positions, so I will look at the pressure at that position and the same here, and I'm looking at the PDF of this pressure. You can see that we have, so this is the PDF of the pressure fluctuation. So it is centered on 0. And here we have a double exponential tails, which was very surprising for me. In fact, I've never seen this before, but maybe we can discuss this. So this part on the left, on the right, sorry, are fluctuations which are higher than the mean value. So this part of the fluctuations will contribute to drag decrease because it increases the pressure at the base. Whereas here, the part which is here, so on the negative part of my PDF, will decrease even more the pressure at the base, so it will increase drag. So these are events that instantaneously will increase or decrease the drag. Okay, so I'm not speaking about the mean drag, now I'm speaking about the drag that evolves in time on the body. So these double exponential tails are very surprising, and usually in turbulence we have reported single exponential tails for pressure, even either negative when we are looking to homogeneous and isotropic turbulence, or positive when we are looking to separated flows. It's maybe it's a bit of mix between the two, I don't know, but this is very strange. Now, if I'm introducing free stream turbulence, I will not change so much the topology of the distribution of pressure on the base, but I will change the values. And you can see that I will increase quite a lot at the same time the mean value. So if I'm increasing the minus mean value, so I'm decreasing the pressure, so I'm increasing the drag, obviously. And also, I will increase quite a lot the fluctuations. So this tells me that the free stream turbulence is increasing the drag due to these mechanisms on the base. And now, if I'm looking to the same PDF as previously, what will happen? In fact, in black, you still have the PDF coming from the no free stream conditions, and in white are the values coming from the free stream turbulence condition. And we can see that we will change quite a lot when we introduce turbulence. We will change quite a lot the fluctuation on the positive part of my PDF. Whereas this one on the negative part are changed, but not so much compared to the opposite. And this is represented by this rectangle in gray, just to show you that there is a difference in terms of effect. So mostly what I can see also is that here the black line, dashed line, represents the Gaussian distribution. So my free stream turbulence will tend to Gaussian distribution for my pressure fluctuation. Very surprising. And we were thinking that, okay, if we change this part, then we change the intensity of the events that will decrease drag. And we don't change so much this one. It means that I will have less events decreasing drag, and maybe it will affect the mean value. But unfortunately, here I am in log variable. So this integral here represents roughly 3% of the mean only. So it means that it doesn't account for all of this story that I have shown before. So there is something else to understand. So that's why here it's interesting in terms of physics, but it is not complete. If we now look, and I will finish with this slide, if we now look to different over positions, we see pretty much the same effects. So we still have these exponential tails that we have for the no free stream turbulence conditions. And what's happening when I'm introducing turbulence inflow, then I will decrease mostly this one. I'm often increasing the negative part of my PDF. So I'm favoring events that will finally increase the drag. And for every position we have tested, we will tend to the Gaussian distribution as far as the turbulence will be implemented. But as I said, the rare events counts for less than 5% of the mean, so it doesn't explain the whole story. Okay, let me summarize the main conclusion of the talk. So we have tried to get a better insight about the aerodynamics of road vehicles in realistic operating conditions, let's say. We have started with a very simplified model where we have used a physical analysis based on a weight survey, comparing experiments and numerics. We have identified the role of the pressure and the Reynolds stresses on the mechanisms that can affect the drag of the vehicle. And we have identified the effect of the topology of a recirculation region. We have extended this analysis to a more realistic condition. So we're using an industrial model with free stream turbulence conditions. What we have seen is that the turbulence, the external turbulence, in our case, leads to drag increase. It changes the Reynolds stresses quite a lot, but finally, this Reynolds stresses evolution doesn't account for the overall drag increase. And that's why we have looked to pressure. We have seen that pressure fluctuations tend to Gaussian distribution when we impose turbulent condition at the external in the external flow. But still, we need to complete this to understand fully what's happening. So this brings me to some continuing work. First of all, here we have only one type of turbulence that we have used. What will happen now if I'm changing the integral scale or if I'm changing the turbulence intensity? So this is something that we need to investigate in the future. A big problem will be also to be able to reconstruct pressure. In our case, we will try to make it from PIV datasets. So we have already published something on this. But in the case of the realistic model, it's a bit more tricky because we need to include the fact that the geometry has curved boundaries. So maybe here we will have to implement some kind of emerged boundary method to be able to make this. And also we need to take into account the 3D effects. 3D effects is how can I get from the analysis I've done today to this type of flow, which is a bit more complex to do. And if we think in terms of experiments, it's very tricky, in fact. And this is coming from an experiment that we have done quite recently, but it's painful. Here, all the things I've done here are done using an average. This is an average because I'm looking to the average drag. But when you drive, you experience drag which is varying in time. And then it's interesting because your flow conditions can change. You can have traffic or not. So this will make you there is a life around your vehicle. So I think at some point we need to go one step further, doing scale by scale analysis, implementing some kind of more physical understanding of what's happening. This is very complex. This is very complex, and even if we think in terms of experiments. And there is something maybe to do with the connection with the rare events that we have seen for the PDF of the pressure at the wall, maybe. And all of this, at the end of the day, could be obviously very useful to design efficient flow control strategy, because at the end of the day, you want to minimize your drag. That's at least how you will sell efficient car in the future. So that's, I think, all for me. Yeah. Thank you for your attention. And if I have any question, I can try to answer it. Thank you.
So thanks, Nicolas, for the very interesting and very comprehensive presentation. I would, as you said before, I would just open the floor for questions. So whoever wants, I see already Jacques who opened his camera. Maybe you want to ask a question.
Yes, you hear me?
Yes.
Yes.
Yes. I have one question on each side. Thank you very much, Nicolas, for your talk. Hi. The first question I wanted to ask is about the RRI. So the slides 18 and 19. I wonder if this surface is always a closed surface. In 3D situations, if you have some kind of conical vortices or mean fluxes through the surface.
Sorry. Let me maybe show you. I will do it like this. Do you see my screen?
Yeah. So it's it was 19 or 18, something like this.
Yeah. Okay.
Sorry.
That's a good point. At the beginning, in fact, we have tried to use another interface. We have tried to use the turbulent non-turbulent interface because it's let's say more common in literature. And this was a bit difficult when you are in the near region of the vehicle. So that's why we have looked to this recirculation region interface, which is just an extension of what we did on the ramp. You remember this maybe with Francesco Stella. Okay. So I will present you maybe the results coming from the experiments in 3D. So this is the experiments that we have done. So it's on the Ahmed body, where we have made a lot of stereotypy plane in the vertical and the horizontal directions. And at the end of the day, by an interpolation in 3D using a lot of image pairs, we have been able to reconstruct this mean flow on which we have been able to build a recirculation bubble. So this is an experiment that we have done. So it's a 3D recirculation bubble.
RRI.
Yes, that's the RRI. That's the RRI in 3D. So you can see that there is still some small problems at some point, position and so forth, but at least in average, this interface is closed. Now, instantaneously, I have no answer for you right now. That's why we are looking to the numerical simulation. Okay. So the Reynolds LES approach, because in that case we can define and see if it's closed or not for every instantaneous measurements, let's say. But getting a 3D interface instantaneously in a simulation is also a tricky problem.
Yeah. And here you miss a portion of the back of the car, of the model, which is about 10 to 20%.
Yes, because the bubble is not covering fully. Here, for example, you can see this is coming from a simulation.
Okay.
You can see that the recirculation bubble doesn't cover the entire base, which is something which is common on the Ahmed body.
Okay, but is it okay? Your reasoning is okay, even if you don't capture the full back of the body. You think it's the drag because you speak of the CP on the reduced surface on the body.
Yeah,
here,
if I remember, here we've got something like 80% at the total of the surface. So it misses parts which are here, obviously, but at least the main scenario remains valid. Let's say.
And can I ask a question about the second part?
Yes, sure.
I have always, thank you very much for all these rare events presentation, but just wait, on the slide 38, just before, because my question is much more basic, 38, where you present the CD variation or the forces variation. I have always a question on this, because if you put decaying isotropic turbulence, the scale, the length of the body is about 1 meter.
Yes.
And it's not negligible. So have you some aerodynamics is called buoyancy effects, because the static pressure increases? And do you correct for them?
Yeah, we correct for this one.
Okay.
We correct for this one. It represents something like 0.2% on the drag, in fact. That's very small.
Very small, okay.
What we have to be, so for the drag itself, it's small. But that's a good point that you have. We need to compensate for the pressure, the free stream pressure measurements. In our case, I'm not sure I have it on the schematic, but I will explain quite easily. Let's say here, do you see my screen?
Yes.
In fact, in our case, the P infinity is measured at that position, roughly, let's say, okay? And since we have turbulence which is decaying, then that's just a Bernoulli problem, in fact. We have here P infinity, which is here, which is different from the measured one. And this one we compensate also for, and this correction is much more important compared to the drag itself.
Okay.
So we need to be careful about this, but you're right. We compensate for, we have some corrections due to the turbulence itself.
Okay, thank you very much.
You're welcome.
So, is there any more? Is there any other question for Nicolas? You can. I remind you that you can just unmute your mic and ask your question, or either write it in the chat and then we'll report it. Well, maybe I can ask a question then.
There is a question here.
I'm going to ask a question about things that you said you want to talk about. You said that with your hybrid LS method, well, you have a much better agreement with the experiments, and also you wanted to run the simulation long enough to have to see extreme fluctuations or by
stability.
Both of them. And the question is how this method, which is not EDNS, how performant is it to represent maybe by stability event that you would also have in experiments? Do you have an agreement between the two, at least qualitatively, between experiments and?
Yeah, that's a big problem. Let's say that the comparison that we've made on the mean flow and the mean quantities are fine. Now on the dynamics, we are still not very happy with the simulation. We are not able to get the bistability at least as strong as in the experiments, clearly. I think the problem is, and this is a recent paper by Amy Morgan from Imperial College, where they have done some LES simulation, so fully LES simulation around, I think it was a Hammett body also. And they have shown that if you don't pay too much attention to the way you solve the flow very close to the wall and close to the front, then you may change the way your bistability is here or not, in fact. So here we are using runs close to the walls because the the hybrid approach is runs where it's expensive and LES where it's not. So I think we miss the problem anyway.
So what do they say that there are some small perturbations in the upstream and in the wall that kind of trigger your event?
That's at least what is in the paper that I was mentioning, the one of Amy Morgan's, where we have let's say implement or not perturbation in the front part, and they can trigger or not the bistability.
So, but what do they mean by trigger? Do they? The question is, the fact that you generate two distinct flow continuities.
So there is no bistability or there is bistability. That's all. There is no transition, regular transition between the two.
So the thing, either you can resolve or not the fact that you have two bistable flow configurations, and you can also change let's say the frequency or the time that you have to wait between the two.
Maybe I'm not sure about this. To be honest, I don't know the answer for this one. But for the experiments, at least, usually we have the same time of trends for the time of change between the two modes, in fact. For the C4 model, we don't have any bistable effect in the experiments. Yeah, it happens only for the embedded body, in fact. Did I answer your question? Yeah. Thank you. Yeah, Christos?
You said that the shape of the bubble is the same whether you have or you don't have free turbulence.
Before.
The shape of the bubble, the average shape. That's the average shape.
Yeah, that's even okay.
However, I assume that if you have free turbulence, this bubble fluctuates much more than.
That's a good point. When I prepared the presentation, I thought to myself, I need to make a PDF for the bubble shape, something like this, to be sure that there is no effect on the fluctuations. So this is something I need to do when I go back.
But in effect, because perhaps it relates to the Gaussianization of the pressure.
Yeah, you're right. I think there is something to look at this one. I prefer to do this on the data set we are now post-processing, where we have much more images compared to this one. I'm here with 1,000 images. We still have some problem of convergence on some quantities. So I prefer to wait for the other one. But it was done with 225 megapixel cameras. So the data set itself is very huge. We have some tons of data, and the post-processing is long also. But this is a good point. I think there is maybe something to look to this.
One very simple question at the end. You talked about scale by scale analysis.
Yeah.
You have, are you clear what you mean by it?
Yeah, you mean?
Yeah, what do you mean by that?
Okay. Let's say it's a bit like this, in fact. Today, so this is a work we have done on a ramp. So the flow is coming from the left to the right. So we have a flow separation, and we see here in red the mean recirculation region interface. So that's pretty much the same spirit I've done today in the talk. But if you look to the flow itself, it is this one, in fact. So your PIV is a sort of experimental LES problem. So at the end of the day, this is the real life problem. This is just a filtered view of the problem. So we cannot get every physical insight using only this, let's say, okay? But this one is tricky. So here, if we look to this interface, we can still apply the same problems I have mentioned, in fact, before. We have additional terms, for sure, but there is no reasons. We are using a Navier-Stokes equation, so maybe your equation is more valid to what I would like to do here. So taking account the inhomogeneity, the anisotropy, the unsteadiness, and so forth, let's say. Problem is, if I want to do this, I need to define the interface. And I need to define the speed of the interface. And this is my tricky problem right now. Because we have PIV systems which are not fast enough. And if we have not fast enough PIV system, we cannot track the interface. And at some point, this velocity of the interface has to be taken into account, because if we want to look at the entrainment, That's the difference between the real, let's say the raw signal and the interface displacement problem. So we need to be in the right frame, I think, to be correct. Do you understand what I mean? And if you are going to water, since the speed and the frequency are much lower, that's something that you can do. And Maruzic and so forth, they have done it in water, for example, for the jets and so forth. In air, that's almost impossible with classical system. So we are now thinking about a new system that we can implement to get this velocity and to try to solve the problem. But it's tricky. Thank you.
So I see that there is a participant who raised up his hand. So please go ahead.
Yeah. So thank you for a very interesting seminar. So sorry, did you hear me well?
Yeah, I can hear you.
How's it? In fact, two questions about the numerical method that you use. So you mentioned you use the hybrid and then the range method. I imagine that the hybrid will be more expensive than the range method. That I would like to comment something about that.
Sorry, I missed your point. You wanted to know what?
The simulation cost for the range and the hybrid range areas.
Simulation costs. The hybrid one is more expensive.
Yeah.
The mesh is the same in both cases. In fact, we didn't change the mesh. And the hybrid simulation was initiated using the results coming from the RAN simulation to start from something which is not so stupid. But the main difference between both of them is the time history, because the RANs here was done without time history. We don't see any effect of the time for the RANs, to be honest, in that type of flow here. Whereas the RANs LES, by definition, should be done with time resolution. So obviously the hybrid was more expensive.
Okay. And then
let's say if I remember well, I'm not the expert of this part, but if I remember well, it was something like 3 weeks of computation to get one time scale, one typical time scale, in fact.
And to be sure that, in fact, it's the 3D simulation, and then you just take the 2D plan for post-processing, or it's just a 2D simulation?
Yeah. We've done obviously a 3D simulation, and then we just extract the data at the same position as the PIV to be comparable to the experiments, in fact.
Okay, so you have the 3D effect in your simulation.
Yeah.
Okay.
We don't save the 3D data from the simulation because it's just impossible, in fact. So we make some slice and we extract the data from this slice, in fact, during the time evolution.
Okay.
And then we make the average. That's pretty much like we have done for the PIV, in fact. The approach is the same.
Okay, thank you.
You're welcome.
Maybe Jacques, you want to ask one more question? Go ahead.
Yes. Is it possible for you to get the time scales between the rare events in the tails of the PDF? It would be very interesting to see if this is associated to pumping or some very slow motion of the bubble.
Yeah. That's something that we can do, obviously. The scanner we have used here is a high-speed scanner. We have. Can you hear me, Jack? Okay. It is a high-speed scanner. We've got something like 500 hertz for each channel. So I think we are good for this. The problem right now is the channel was only 64. There is only 64 channel on that scanner. So now we have ordered a new one to get the full base at once, because now we are obliged to we are constrained to change the configurations to make the full base. But you're right. This is something that I would like to see after. And also we have started to make some correlations between points to see if there is any large scale events, also some kind of inhomogeneity and so forth. And we had right now some surprise, but that's interesting. There is plenty of things to do, I think. The problem is, unfortunately, there is no guarantee that what we will see for this type of car vehicle will be applied, could be applied to another configuration. I'm pretty sure it will be geometry dependent.
Okay. Thank you.
You're welcome.
So is there someone else who wants to ask a question? Just feel free to unmute your mic or to write it in the chat. I can report it. So maybe then I can ask a question myself. Then, I mean, you talked about, you just mentioned geometry dependent, let's say, results on the drag and on the wake. I ask myself, what is actually the effect of turning wheels on the on what we see? Because I expect that, I mean, the asymmetry you mentioned before can either be can quite much be affected by the fact that there is an entrainment from the wheels, right?
You are right. There is surely effects. I will be able maybe to answer this question in 2 weeks' time. I have received the GFM paper to review, okay, where they have implemented effect or not of the moving wheels. So I can answer that now because I've just read quickly the first part of the paper. Now I'm going to the part which is more interesting about the wheels. Okay. So, but for sure, I can tell you that they find effect. They didn't make this type of analysis I have shown today, but there is effects on the mean flow and on the Reynolds stresses. So for sure, there is something. Yeah.
Okay. Okay. Because
now having turning wheels in an experiment, yeah, it is just a nightmare.
I can imagine. I know that some experiments actually use a moving, rolling, belt under
rolling belt. Yes, yes.
Yeah.
We've done some experiments on a real car at S2A at Saint-Cyr-l'École, let's say 2 years ago. It's a bit confidential, so I will not speak about this much more than this. But the problem also is that you have to suck the incoming boundary layer. So that's not only the belt itself, but you can have also some vibrations on the belt. So that's very tricky problem. I know that very close to here at Lamy, they have implemented this in a wind tunnel, I think, Lancarsbrook. So this is something that will be very interesting in the future, but very complex to implement.
Okay. Okay.
But for sure, there is an effect.
Okay. Okay. Thanks. And if okay, if there is someone else there who wants to ask a question, please go ahead.
It was about the presence of on automobile, because I imagine that if you have moving wheel, you also have the vehicle which moves with respect to the ground, so that you have some the flow is not the same if you have just a fixed vehicle, fixed ground, moving wheels, or somehow moving grounds, moving wheels.
Yes, that's why, for example, in Saint-Cyr-l'École, they adapt the speed of the belt to the speed of the wheels. So that's you need to pay attention on this. Obviously, yeah. Did I answer your question?
Yes.
Yeah, and my second point, which of course, I mean, that may be somehow quite important in a few years. There is, I would say, there may be a major difference between the aerodynamics around like a thermal combustion car and the aerodynamics around an electric car, simply because when you cool down the battery pack in the electric car, maybe you can use that flow that you cool with to control somehow the wake, or to address it on the back side of the car, such that you kind of manage to either reduce the drag or somehow control the separation on the backside. Is there some research based on that, or somehow that investigates this effect and its effect on the drag? Or I mean, the question at the end is, can an electric car, for the fact that you are gonna use a cooling system that's that can affect the afterbody wake, be more efficient in terms of drag than most of the cars we see nowadays?
Yeah, you can think. You have to be clever anyway. I mean, I would say, because the car industry, they will not spend so much money in terms of implementing new systems. If you have already something that can be used and just transported somewhere else to be used for flow control, I think that's fine. The problem is that after, you need to have a fan to transport the air, for example, and so forth. And they just that's just painful for them to spend €1 about a new system. They tell you just because we were also interested into. Okay, here we are looking to turbulence, external turbulence effect on the road vehicle. You need also to have some kind of sensors on the vehicle to tell you that there is something happening. Okay, and then you can react to something. Yeah, that's the principle of flow control. Anyway, the problem is that they tell you that the sensor should not be more expensive than 10 centimes of euro. I mean, that's the problem for the industrial. So you can be clever and use plenty of things. Here, for example, we use the microjets to control the flow, but effectively, if you have hot air somewhere that can be used and transported, maybe it will be efficient as this one, and so forth. So that's something in the future maybe we will see. But I'm not sure that if the technology is too expensive, then it will not be used in the car. That's for sure. Maybe Jacques can tell more than me on this, in fact.
Okay. So we may see if there are some more questions to the participants. Just feel free to unmute your mic or write in the chat. I will report the question. No, that doesn't seem to be the case. Is there someone in the room who wants to ask a question?
Everybody seems exhausted.
Okay. Okay, then thank you. Oops. Thank you very much for this very interesting talk.
Thank you.
It's
my pleasure.
Talk, and thanks for answering the questions. And I invite all the participants to thank our speaker. Thank you once again, Nicolas.
Thank you.
Then I wish you all a good evening and hope to see you soon in a week.
Bye-bye.
Bye. Bye-bye. Thank you very much.